Welcome to our lectures on flexible AC transmission system. Today we will continue our discussion with triple SC, remaining part of it. Thereafter we try to also discuss about TSSC. So, what we were discussing on previous class. So, let us see that the real power compensation capability of the triple SC. The capability of the reactive line compensations combined with simultaneous reactive power exchange can also enhance the power oscillation damping. So, triple SC can provide the active damping. For example, during the period of the angular acceleration, the TSSC with a suitable energy storage can supply the maximum capacity of the line compensation to increase the transmitted power and concurrently absorb the active power also. So, this is actually the way it can increase the stability and can damp out the power frequency oscillation. During the period of deceleration, when energy comes down, triple SC can execute the opposite operation, opposite compensating action that can apply the maximum inductive compensation to the line to decrease the transmitted active power and concurrently the supply of the additional active power to the line. Now, how SSC can be controlled? Please note that this control technique which we are discussing, it is more or less common for all the series type compensator. As explained, triple SC is implemented by a voltage source converter. So, SSC output voltage control converter may be categorized as directly and indirectly controlled. Same way we have seen in case of the STATCOM. So, directly and indirectly injection. So, same way we have a same kind of thing in STATCOM in case of the triple SC. For directly controlled converters, both angular position and the magnitude of the output voltage are controlled by appropriate value of this actually with this actually voltage control current source inverter. In case of the indirect control converter, only the angular position of the output voltage is controlled by the valve and magnitude remain proportional to the DC terminal voltage. So, you allow that DC voltage to fluctuates. So, we shall see that pros and cons of these two methods. The control method of maintaining a quadrature relationship between the instantaneous converter voltage and the line current vector to provide the reactive series compensation and handle the subsynchronous resonance or SSR can be implemented with indirectly controlled converter. So, you can just control the phase angle, rest it will take care of by the DC bus voltage. The method of maintaining a single frequency synchronous output independent of the DC terminal voltage variation requires a directly controlled converter. So, if you wish to mitigate the sag, then you have a directly controlled converter. Although the high power directly controlled converter more difficult, we shall see the control technique and costly to implement than the indirectly controlled converter. So, indirectly controlled converter is a cost effective solutions in triple SC. So, let us discuss about the internally controlled internal control scheme for the indirectly current controlled triple SC. The inputs of the terminal voltage are, please note that line current, the injected compensating voltage VQ and the VQ star. or VQ capital. The control is synchronized with the line current by a PLL or the phase lock loop. After plus pi by 2 or minus pi by 2 phase shift provides the basic synchronizing signal. The phase shifter is operated from the output of a polarity detector, which determines whether reference VQ is positive in case of the capacitor or negative in case of the inductor or the inductive kind of load. Then the compensating voltage, the VQ, is controlled by the simply a closed loop control. The absolute value of the reference VQ is compared with the measured magnitude of the injected VQ, and thus we have an error and we feed this error to the PI controller. The amplified difference or the error is added and as a correction angle alpha. So, output of the PI controller will be the change of the phase angle, that is del alpha, to the synchronizing signal that is coming from the PLL to theta. So, angle becomes then theta plus del alpha. Depending on the polarity of del alpha and angle theta, consequently the converter gate driver signal based on this compensating voltage VQ will be shifted. This phase shift will cause the converter to absorb real power from the AC system for the capacitor or vice versa, or you can inject the real power if you have a storage capability supplied to that of the AC system from the DC capacitor. So, this is the internal control circuit of the SSSC, and this control circuit is almost common all the 3 types of SSC. So, you have the VQ reference, you then calculate the magnitude of it, generally it is a pre-detected circuit. So, you got a VQ ref and you have the VQ, and from there you have a actually sensors. So, voltage magnitude computer, so that measures actually the VQ. So, you can write capital VQ or VQ star, then it is been subtracted from the actual VQ. Then it is fed to the PI controller. PI controller is essentially an error amplifier, and ultimately there will be few inputs. So, there will be a polarity detector, whether it is a positive phase or negative phase, and accordingly there will be a PLL. So, that will give a phase shift by plus minus pi by 2. So, from there theta will come, theta will added up with actually del alpha from this error amplifier. So, ultimately this become theta plus minus alpha depending on kind of compensation you are doing. Then you have a gate logic to give the firing of the thyristors, sorry it is GTU. We can also use IGBT for the lower rating, and there will be a PLL. From PLL actually we can generate the information of the zero crossing, and from there actually we fit ultimately phase shifter will take input from both the polarity detector as well as the PLL. So, from these discussions of the internal control technique, we can conclude this scheme can be used to eliminate the unwanted voltage component due to the modulation of the DC capacitor voltage by subsynchronous or other line component. That is one of the biggest problem in power system, subsynchronous oscillation, that can be damped out by this SSSC. It also suitable to provide both reactive and the real line compensation if converter is equipped with a suitable DC power supply. So, we have a storage element, that is all. The control structure is similar to that discussed in connection with the indirectly controlled converter, except the continuous and the independent control both of the magnitude as well as angle of the compensation of the voltage is required. So, there will be little change in the control circuit and it will be more complex, and since we have to give a measured value of actually VQ and alpha. So, control technique will differ little bit. So, the synchronizations of the current is accomplished by a phase lock loop. So, we have to sense the current, from there we will actually generate the phase lock loop. The control is operated from the 3 reference signal, that is VQ reference or VQ star, defining the desired magnitude of the series reactive compensation voltage that required to be injected in quadrature with the line. RQ reference, it defines the magnitude of the series real compensating voltage. In practical cases it should be 0, but to meet the losses this has to be fed. And DC reference, defining the operating DC bus voltage of the capacitor. The active voltage reference, this one, V capital Q small q ref will change dynamically depending on the magnitude of the injected voltage, which with the line current determines the the reactive power exchange with the series compensation. So, that is actually the term that will decide the amount of the work compensation with SSSC. So, overall voltage reference for this direct control will be actually VQ R ref plus VDC R ref, which with the line current determines the real power exchange for the proportional real power compensation of the line and for keeping the DC capacitor charged to the some reference voltage. This is the requirement. These 2 reference are compared to the corresponding component of the measured compensation voltage of VQ. From the resulting signals of the magnitude VQ and its angle phi with respect to theta is derived. The magnitude VQ, theta plus phi are then used to generate the gate driver signals to the converter. So, this is the internal control of a directly controlled circuit, and we have to actually have both phi plus theta and the VQ. So, you have to feed both this logic to the gate pattern. So, let us see that what are the difference from its indirect control technique. The real magnitude of the computer actually will compute that VQ, and you have a VQ reference and you have V small q capital Q reference, and from there actually you subtract, you get V small q capital Q. Similarly, you have to have a real power reference, that is VQ R reference, that you will feed, and since you require to maintain a DC bus voltage at desired level. So, from VDC and VDC ref you will feed to a PI controller. This PI controller, this error will be added up, and you should have a actual calculation of VQR that has to be subtracted. So, then you fed this value to the error amplifier. This again from this point of VQ V small q capital Q ref, it fed to the polarity detector. Similarly, there will be and that this input of the polarity detector, whether it is in a positive phase or the negative phase, will be fed to the phase shifter that will make the phase shift 90 degree with the I. So, current. So, similarly there will be a phase lock loop. So, that also fed the input. So, from there actually theta will be generated, and from this error amplifier you will have a actually the both the magnitude. So, essentially you will have a, instead of the one PI controller here, in this case you will have 2 PI controller, and thus you will have theta plus phi will be the effective compensating angle, and you require to inject the magnitude Vq, and that information will be fed to the gate driver circuit, and that will be fed to this actually voltage control current source converter, and that will inject voltage in Vq. We will have this logic plus minus j Vq sigma I by mod I. So, this is the actually the principal operation of direct controlled SSSC, and it is the sophisticated and the most advanced series compensator. It compensates very accurately the amount of the reactive power, and also it can actually inject the amount of Vq required in different purpose of operation. So, what we can conclude from this control circuit discussions, in the previous sections variable impedance type of the synchronous voltage source type compensator has been discussed. Again we shall discuss another impedance type compensator after this class also. The type of compensator compromising of the power circuit related to the internal control has been discussed. The compensator have a different operating principle and exhibit actually differing the compensation and performance characteristics. So, it will have a different way to of control. We have seen that actually impedance control is very simple. So, you have to control the actually delay angle of the GTO, so that actually turn off angle of the GTO in case of GCSC. But here its control is quite complicated. You have to have instantaneously fitting that value of the Vq and the phi. From there actually getting pattern will be controlled. So, actually as if we have discussed this in while discussing this fax devices, we have discussed few control technique of the voltage source inverter. You can see that actually space vector is best fits to this solution. So, we will provide, we shall try to fit actually the space vector modulation technique for basically SSSC. So, they all can provide series reactive compensation, all, whether it is impedance method or the voltage controlled or you are injecting voltage source, both can control the series reactive power compensation, and we operate it self sufficiently and input reference defining the desired compensating voltage and reactance. Therefore, for the external control that defines the functional operations of the compensator are same for all type of the series compensator discussed. Ultimately it will inject some amount of the VAR to the system. So, it is whether it is impedance method or the voltage method, the actually externally they looks equal. So, in internal control the main power flow control is executed by a slow closed loop, which is operated from one of the selective reference, that is XQ ref, IQ ref, V ref or P ref, whatever may be. The corresponding to the network available, the XQ, VQ, I or P is derived by the voltage current processors and compared to selected reference. The amplified error at the output of the PI controller provides the reference VQ and the XQ and the VQ for the internal control. The auxiliary control signals is also there to improve the transients that will be discussed soon, dynamic stability, and to damp out the subsynchronous oscillations are derived with the derived from the relevant system variables, that we will see soon. So, this is the overall structures. So, this is basically for the transient stability, this is for the subsynchronous oscillation, this is for the power frequency oscillation damping. So, and this is the modus operandi of different mode of operation. So, this is the overall external control circuit for the any kind of series compensator. Ultimately, you have V I, V and VQ, and from there you will process the data what you require to compare. And thus an operation mode selection can be as follows. It can be XQ if you want that actually for the impedance mode of operation, there you want to actually inject the value of the VQ by value of the XQ, and if you have to have a voltage mode of operation, you will choose the value of the maybe the VQ. So, similarly you can choose the IREF as well as the power ref. So, accordingly you will actually have a control. So, both will be controlled and compared, and ultimately it will be fed to the PI controller, assuming that these disturbances are not there. We shall take these disturbances after that. So, thereafter what happen? So, we will feed it to the PI controller, and from there actually we actually have a measured value of the VQ and the or XQ, and that will actually will insert the series impedance or the series voltage into the system. And if you have these problems, if there is a change in frequency, so that means the power oscillation has to be damped out, and from there actually you will feed this input whether power in the system is actually oscillatory or constant, and also there is a variation of frequency or not. From there actually then the term power oscillation damping will come into the picture, and ultimately you will feed this value. You can know that you can write it out the differential equation, we shall show in the next class, or we shall give you some assignment on it, that it will be a second order system, undamped second order system. So, we have to add the damping, and ultimately this TSSC or this kind of series compensator can add the effective damping. So, what will happen due to that actually, so it will be adding up some amount of the signals to this PI controller, and it will be, this input will be fed, so that it will mitigate the oscillation of the del f. Similarly, when you have a subsynchronous oscillations that require to be damped out, so you will change this alpha in such a way that will damp it out. So, so del phi, if there is a change in del phi and there is also the frequency oscillation, then it leads to the actually subsynchronous oscillation. This information also will be fed to this actually the summer block, and it will be fed to the PI, and thus it will actually try to mitigate the subsynchronous oscillation. Then you have to enhance the transient stability. If the transient is present, so you require to increase the power handling capability of the line, and thus for this reason these blocks adds up directly with this actually the summer. There is no input to the PI controller. So, it will be increasing the overall power handling capability of the line, and thus or increasing or it will change if the power demand is sinking. So, accordingly it will change this value, and this will actually feed this through the gate logic circuits of the impedance or the voltage source converter, and accordingly it will generate the VQ. So, this is the external control circuit, and this is this actually theme is common for all series regulator. So, what we have already discussed this and this now we have left with another series control regulator, that is actually series thyristors control series capacitor. So, we shall continue with it now, and we shall also try to, we will continue with the next class, because it is time left is very small now. The basic circuit arrangement of the thyristors switch capacitor, basically see the logic here. You know, you will have a series capacitor and there is a anti-parallel thyristor connected with it. It is just is a very just the opposite of this actually TCR. So, we know that actually thyristors has to be put in parallel with the capacitor, for this it is put parallel to the capacitor. If you wish to short this capacitor, then actually you put this alpha is such a big that it will almost short this capacitor. If you do not trigger this thyristors, then total capacitor will be injected to the system, and accordingly if you will change the alpha triggering angle or the delay angle, then the value of this actually the capacitor, subsequently the voltage across it will change. So, this is the way you inject different amount of the voltage VQ in the into actually the line voltage. So, the basic circuit arrangement of the thyristor switch series capacitor, that is TSSC, is consist of the capacitor shunted by a valve and composed of a string of the reverse parallelly connected thyristors in series. It is similar to the circuits structures sequentially operated GCSC. So, there is not much difference, but it is thyristor operated, but its operation is different due to imposed switching restriction of the conventional thyristor valve. So, you can turn it on, you can turn it off. Since GCSC is mostly controlled by turn off, so principle of operation here will be different, because turn off is not in your hand. So, degree of the series compensation is controlled like a step manner by increasing or the decreasing the number of the series capacitor inserted into the line. Capacitor is inserted by turning off, and it is bypassed by turning off the corresponding thyristor valve. So, you actually change the current through the capacitor, and thus the voltage across the capacitor by changing the delay angle. Thyristor valve commutes naturally. So, this is for this it is very simple circuits, that is turn off when current becomes 0 across those devices. Thus, a capacitor can be inserted into the line by the thyristor valve only at a 0 crossing of the line current. So, this is the principle of operation. So, please recall that we had a 0 voltage when you turn off in GCSC. Since the insertion takes place at a line current 0, a full half cycle of the line current will charge the capacitor 0 to the maximum voltage and 0 to the maximum, and successive opposite polarity half cycle to the line current will discharge from maximum to 0. So, see this curve. So, this is basically I, and this one is Vc. So, you see that Vc will again become 0. At this moment actually voltage was 0 because thyristors was triggered, and at this moment thyristors was put off, and thus what happened actually it swells up, goes to the maximum voltage Vc. Thereafter again when current becomes 0, then voltage becomes 0, and subsequently again here Vc will be 0. So, this is the oscillation pattern across this voltage capacitor. The capacitor insertion at line current 0 necessitated by the switching limitation of the thyristor valve results in a DC offset voltage. This is one of the problem. You see that there is a DC offset voltage. Ultimately, if you take the peak and ultimately it is shifted here, and this will change, while actually this current is going actually positive to negative, and for this you have negative DC offset. If you actually just in this moment you can find that you may have a positive DC offset. So, we shall continue to discuss TSSC in next class. Thank you for your attention.